Hello, in this video we are continuing our discussion of section 8.3 on the integral and comparison tests. Specifically in this video we are concentrating on the limit comparison test. So the limit comparison test is similar to the direct comparison test in that you have to come up with a comparison series. You do some stuff to that comparison series, you figure out what the end behavior is, you figure out a certain relationship between the comparison series and the original series, and then based on that relationship you come to a conclusion about the original series. The difference between the limit comparison test and the direct comparison test is that that relationship has to do with a limit instead of an inequality. Now, most of the time, evaluating a limit is easier to do than establishing that inequality. So if you were having to choose between applying either the limit comparison or the direct comparison, I would probably say pick the limit comparison. But there are times when the limit comparison test is inconclusive. So if you can't get that correct limit relationship that you need, then perhaps try applying the direct comparison test. But in this case, we are going to apply the limit comparison test, so we need to start by coming up with our comparison series. We come up with the comparison series the same way for the limit comparison test as we do for the direct comparison test. So this means that we are going to take our largest variable term in the numerator. So for this one, that is k to the fourth. We're going to take our largest variable term in the denominator, which is 2k to the sixth in this case. So then if we simplify this, we'll get the sum from k equals 1 to infinity of no k in the numerator, 1 over 2k squared. Now this, we can pull the 1/2 out in order to find the end behavior of this series. If we pull the 1/2 out, we'll get 1/2 times the sum from k equals 1 to infinity of 1 over k squared. This is a p-series. Even though we have a constant times a p-series, it's still considered a p-series, and that constant isn't going to change the end behavior. So p equaling 2 in this case, which is larger than 1, means that our comparison series converges. So then we look at the limit as k goes to infinity of a sub k over b sub k. Now remember, the numerator is your original series, and the denominator is the comparison series. This isn't always absolutely important that you do the original divided by the comparison. Sometimes you will still get a correct value, specifically when you're talking about case 1 of the limit comparison test, but sometimes you will need it to be in this order for your ratio. So I would recommend just always putting the original on top and the comparison on the bottom. So we're going to evaluate the limit as k approaches infinity of k to the fourth minus 2k squared plus 3 all over 2k to the sixth minus k plus 5 all over a comparison series is 1 over 2k squared. You could actually get away with doing 1 over k squared as well, since you've moved the 1/2 out. It doesn't really matter for the limit comparison. It does matter for the direct comparison. You want to keep that constant with the direct comparison test so that it's easier for you to get the inequalities that you need. So my recommendation is just always keep the constant there, okay? It will always work if you always keep the constant with your comparison series. So now we're going to simplify this. This will equal the limit as k goes to infinity of, I'm going to multiply by 2k squared here, and distribute that to the numerator, so I'm going to get 2k to the sixth minus 4k to the fourth plus 6k squared all over 2k to the sixth minus k plus 5. Now since k is going to infinity and we have a rational function here, what we can do is look at our highest powers in the numerator and the denominator. Since our highest powers are the same, what we're going to do to evaluate this limit is we're just going to pick up the coefficients in front of our highest powers. So this is going to equal 2 over 2, and this is because the highest power in the numerator equals the highest power in the denominator. If the highest powers are not equal, then you don't just pick up the coefficients. Those are different cases. If you want to review those, you can look at, I think it is section 1.6 in the book when we're talking about limits involving infinity, okay? So 2 over 2 does simplify to 1. This is our L value. Since our L value is, which is 1, is, sorry about that, let me see, since our L value, which is 1, is between 1 and infinity, and our comparison series, which is the sum from k equals 1 to infinity of 1 over 2k squared, converges, then the original series, the sum from k equals 2 to infinity of 2k, oops, sorry, not 2, k to the 4th minus 2k squared plus 3 all over 2k to the 6th minus k plus 5 converges also. And this is by the limit comparison test. Remember, if the problem doesn't specifically tell you to use a certain test, then you need to state which test you're using. You can do it either in your concluding sentence at the end, or you can do it at the beginning when you choose to use that particular test. And again, after we finish talking about all of the comparison tests in the next section, sorry, not comparison, all of the series tests in the next section, then I will talk a bit, or at least the lecture will present some information about how you should choose between the different tests. Also, a bit of encouragement, you won't have to remember all of the details of all of these different tests. I will be giving you a series test summary sheet. But again, I'll get into that more in the next section. For this example, we have that our final answer is that the series converges by the limit comparison test.